Welcome to the Deep Dive. We're here to give you the shortcut to being genuinely well-informed. Today, we're digging into just one really detailed source, one that might just change how we think about who the future energy players are. We're looking closely at the analysis in exploring the Shetland Islands' potential as a green e-hydrogen export hub for Europe. Our goal is to figure out if this pretty remote group of islands up north can genuinely shift from its oil and gas history to being a cornerstone for Europe's green energy future. The backdrop is something we talk about a lot, this urgent need for the EU to hit its 2050 net zero targets. And that means needing huge amounts of clean energy imports because, honestly, densely populated bits of mainland Europe they struggle to generate enough renewable electricity, RE, for everything.
That's exactly right. And this study puts Shetland under the microscope because it has two big things going for it. One is geography. It's relatively close to the big European markets. And two, it has access to incredible renewable energy resources, largely untapped. The study is all about Shetland's potential to become a massive exporter of green e-hydrogen. That's hydrogen made using only renewable electricity. They're looking out to 2050. And they've modeled three quite different scenarios for export potential. Really, we're trying to get answers to two key questions. How much green e-hydrogen could Shetland actually produce competitively? And crucially, what would it cost to get it delivered to Europe?
Okay, let's unpack that a bit. Why hydrogen specifically? I mean, green e-hydrogen. Why is it the fuel Europe needs to import? Couldn't they just import the electricity directly?
Well, it's because hydrogen is this incredibly versatile chemical energy carrier. We need it for the really tough sectors to decarbonize. Think about specialized fuels like ammonia for shipping or sustainable fuels for aviation. It's also a core ingredient, a feedstock for chemicals, plastics, fertilizers, and maybe the biggest one, heavy industry, steel making, for instance. It's responsible for, 7 or 8% of global greenhouse gas emissions right now?
Wow, yeah.
You can't just plug a steel furnace into the wall, You need hydrogen to replace coal or coke in the process.
And Europe's appetite for this stuff is just massive, isn't it?
The numbers are pretty stark. The EU's target for 2030, which isn't that far off, is 10 megatons produced domestically and another 10 megatons imported.
10 million tons imported. How much energy is that?
That import target alone is 333 terawatt hours, TWH. But looking out to 2050, some forecasts put the demand for e-hydrogen over 4,000 TWH.
4,000, okay.
So yeah, massive imports aren't just nice to have, they're basically essential.
Which brings us back to the supplier, Shetland. What really makes it stand out? Because, for most people, it's Shetland ponies, maybe oil rigs, fishing, not exactly a green energy powerhouse in the public mind.
No, it definitely seems like an unlikely candidate on the surface. It's about 150 kilometers off the northeast coast of Scotland. Tiny population, maybe 23,000 people. And yeah, historically, its economy is built on oil and gas, fishing, farming. But here's the twist. It's got this geographical edge plus the resource base. Shetland has truly excellent wind potential. And importantly, really significant wave energy potential too. And things are already happening. There's the Viking Energy wind farm, that's 443 milliW onshore, and the Orion project, which is specifically planning large-scale green hydrogen production using wind power. And that proximity matters. It's only about 900 kilometers or so to key markets like the Netherlands.
Okay, so the argument in this study is, even if the wind power itself isn't quite as dirt cheap to generate as, say, giant solar farms in the Sahara or Australia, the fact that it's so much closer means the transport costs are way lower, making the whole package competitive.
That's precisely the idea. Resource abundance meets geographic proximity. It creates this kind of economic sweet spot because moving energy, especially hydrogen, which needs compression or liquefaction, gets expensive over long distances. Shorter routes really help. So, to really understand the 2050 export idea, this study first sets the scene by looking at Shetland's own energy transition. They modeled 2019 as a baseline and then a 2035 scenario.
Right, so what was the starting point and what's the midterm goal look like?
Okay, so 2019, pretty much what you'd expect. Heavily reliant on fossil fuels for local energy, lots of waste heat, inefficient processes, not very electrified, costly and polluting.
Got it. And 2035?
2035 represents a big shift. The model assumes Shetland becomes completely energy self-sufficient and carbon neutral by then. This relies mainly on onshore wind, about 467 milliW, plus some solar PV. And the gains are huge just from electrification and efficiency. The model shows total annual system costs dropping by almost 60% compared to 2019.
60% lower costs. Wow.
Yeah. And it's worth remembering, Shetland's already connecting to the mainland grid. There's a big high voltage direct current HVDC cable planned to be live in 2024 for exporting power. So that infrastructure thinking is already there.
Okay, so that's Shetland sorting its own energy needs.
Sure.
Now, for the really dramatic part, the leap to potentially being a global energy exporter by 2050, this study looked at 3 scenarios, right? And they weren't just using the land, they were looking out to sea.
Exactly. And the scale difference between the scenarios is pretty vast. Scenario 1 is the most, let's say, conservative. It sticks to onshore resources, 750 milliW of wind, 1.6 gigaW of solar. Manageable scale.
Okay.
Scenario 2 then adds offshore resources, specifically focusing on wave power, a massive 111 gigawatts of wave. It's a lot.
It is. And then scenario 3 is what they call the all-in approach. It takes everything from scenario 2 and adds another 75 gigawatt of offshore wind power. Highly ambitious. Hold on. 75 gigawatts of offshore wind. Just to put that number in perspective for everyone listening, that's way more than the entire current offshore wind capacity of most major countries combined. How is that scale even conceivable for islands with only 23,000 people?
Well, that's the central question, isn't it? The study is looking at the technical and economic feasibility. It assumes significant advances in floating offshore wind technology deployed far out at sea. It really hinges on whether the massive capital investment required can be justified by the sheer volume of hydrogen you can export. It definitely requires a belief in future tech cost reductions, but the raw resource, the wind and wave energy, is undeniably there.
Okay, before we get to the final cost numbers, let's quickly clarify the units we're using.
Right.
We see TWH2 LHV for volume and euros per MWH for cost. Can you just ground those for us?
Absolutely good point. TWHH2 LHV is terawatt hours of hydrogen based on its lower heating value.
Yeah.
It's basically the standard way to measure the usable energy content in the hydrogen being traded. How much energy bang for your buck, effectively. And the cost, MWH, is just euros per megawatt hour. That's the common unit for comparing energy costs globally, whether it's electricity, gas, or hydrogen. And just for a rough comparison, industrial natural gas prices in Europe, well, they've often been significantly above 70 euro MWH recently. So this study is trying to show green hydrogen can compete.
Perfect, thanks. Now let's get to that core finding about cost versus scale,
Yeah.
the bit that seemed, well, counterintuitive.
Right. So the results are actually pretty striking when you compare the scenarios. Scenario 1, the onshore-only one, produces the smallest amount of hydrogen for export, about 3.5 TWH. Now, the production cost, making the hydrogen itself, is lowest here because onshore wind is cheaper to build. Makes sense.
Yep.
But because the volume is relatively small, the pipeline needed is also smaller, and pipeline economics means small pipes are much less efficient per unit transported. So the transport cost shoots up. It's nearly 49 euro MWH in this scenario. This leads to the highest final delivered cost. 88.4 NWH.
Oh, okay. So cheap to make, but really expensive to ship because you don't have the scale.
Exactly. Now, contrast that with scenario 3, the all-in offshore one. Huge volume, over 626 TWH. Here, the production cost is higher, no doubt. Offshore wind and wave power are expensive technologies to install right now.
Right.
But because the scale is absolutely massive, you can justify building a really large, efficient pipeline. The transport cost plummets. In scenario 3, transport is only about 15% of the final cost, down in the range of 12 to maybe 22 euro MWH. And the result, a final delivered cost of 77.6 euro MWH, which is actually cheaper than the smaller onshore scenario.
Okay, that's the headline finding, isn't it?
Yeah.
This study argues, and they note it's the first time this has been documented in the literature like this, that delivered green hydrogen from these big offshore projects could actually be cheaper than from smaller onshore ones. Simply because the massive scale makes the transport via pipeline so much more efficient, it completely outweighs the higher initial production cost. Scale is everything here.
It absolutely is the dominant factor. The economics of pipeline transport are just transformed at that kind of throughput. You need the vast offshore resources to justify that scale. And that final cost, between roughly 70 and 78 euro NWH is competitive. As we said, it's potentially cheaper than gray hydrogen was costing recently. And it puts Shetland right in the ballpark with other projected 2050 import options, like potentially from Denmark or even North Africa, which are further away.
Let's talk about that pipeline for a second. It's proposed to run, about 1,159 kilometers from Shetland down to the Dutch coast. In those really big scenarios, scenario 2 and 3, where do the main costs lie? Is it the hydrogen fuel itself, the transport, or building all the kit?
It's overwhelmingly the initial capital investment,
Yeah.
building the huge offshore wind farms, the wave energy converters, and all the electrolyzers needed to make the hydrogen. That's where the vast majority of the cost is. The transport cost, while still significant in absolute terms, becomes a much smaller percentage of the total cost per unit of energy delivered thanks to that scale.
Right.
And if you think about the bigger picture for Europe, getting such large volumes from a nearby partner like Shetland, well, that really boosts energy security. Plus, it adds diversity. Wind and wave power from the North Atlantic complements solar power from, say, Southern Europe or North Africa, which helps balance energy supply across different seasons and weather patterns.
Yeah, that diversification and closeness definitely adds value. Reliability is key.
Okay, but every grand plan has its challenges. What are the main roadblocks this study flags up, especially given the sheer scale involved?
The biggest one, and honestly maybe the most eye-opening non-technical finding, is about the people, the local community, and the workforce. Remember, Shetland has only about 23,000 residents today.
Right.
Scenario 1, the smaller one, would create maybe 1,700 jobs. That seems manageable. But Scenario 3, the all-in one, the study estimates it could require a workforce influx of up to 80,000 people by 2050 for construction and ongoing operations. 80,000. That's almost 4 times the current population landing on the islands. That's not just a challenge, that's a complete reshaping of the place.
Does the study offer any thoughts on how you'd even begin to manage that? Housing, schools, infrastructure, preserving local culture.
It acknowledges it's a massive, massive issue. There's real potential for significant local opposition, fears about losing identity, being overwhelmed. The study frames it mainly as an economic opportunity that needs incredibly careful planning, housing, services, integration strategies. But yeah, pulling off something on that scale would need unprecedented levels of local consultation, buy-in, and probably huge government support to manage the social and infrastructure impacts. It's a really big question mark.
A huge one. And then there's the politics and paperwork side, the regulatory stuff between the UK and the EU post-Brexit.
That's another significant hurdle. Even though the UK and EU energy systems have similarities, there are specific conflicts around hydrogen exports. The EU has quite strict criteria for what counts as green hydrogen for imports, rules developed partly after the UK left. And at the same time, the UK's own support mechanisms, like its contract for difference scheme, currently don't apply to hydrogen that's produced specifically for export.
So, a mismatch in rules.
Yeah, and another layer is certifying the greenness. You need mutual recognition of guarantees of origin, GOs, so the EU accepts the UK's proof that the hydrogen is truly renewable. That mechanism doesn't exist yet between the two.
So the physics and the economics might line up, especially with scale, but the human impact and the cross-border regulations are major friction points.
That sums it up pretty well. But the study's conclusion isn't that these are deal breakers. It suggests they are hurdles that can be overcome with negotiation and proactive planning. The potential economic and energy security benefits are just too large to dismiss easily.
Right, so let's bring this all together. This deep dive into exploring the Shetland Islands' potential as a green e-hydrogen export hub for Europe suggests a really ambitious but maybe plausible future. A future where this small archipelago could be sending up to, 626 TWh of cost-competitive green hydrogen to Europe by 2050. And the key insight seems to be how massive offshore scale flips the usual cost assumptions, making pipeline transport incredibly efficient.
Absolutely. I think the main takeaway is that this study provides a really detailed blueprint, a case study, not just for Shetland. It's relevant for any remote region or island around the world that has huge untapped wind or wave resources. It shows a potential pathway, technically and economically, to turn that isolation into a strategic advantage in the future energy system. Assuming, of course, those significant social and political challenges can be navigated successfully.
So thinking about what this means for you, our listener, if a place like Shetland, tiny population, remote location, can potentially generate and export this much zero-carbon fuel by harnessing the power of the sea around it, how might that fundamentally change what we think an energy superpower looks like in the decades to come? That's something to mull over.